So this is going to be the first of three talks on bulk rock databases. It doesn't want to go.
The mouse. Yeah, sorry.
It's because I tried playing with the.
Oh. Yeah.
You're all good now. You can do it.
Yeah, sorry, thank you. And I compiled a database some while ago, and it was, which included the Alaska-Aleutians, that was part of a global project of collecting arc melts with the idea of understanding the origin of the really high silica melts that give us the highly explosive eruptions. We talked a lot about eruptions here, but these were fairly small, so highly explosive eruptions, those that have global effects for several years. And also the silica-rich rocks still make up the bulk of the erupted volume. So I compiled data globally. It was not intended to be comprehensive for all the single arc segments. That's something like the Alaska-Aleutian, just representative. And the focus was definitely on samples that had combined data sets of major elements, trace element, and in particularly the radiogenic isotopes. I took out the duplicates, linked them to a single volcano. These are the results for the Alaska-Aleutians arc. All colored dots do have data. Most of them, I think 52 of these volcanic locations have isotope data, but not many of them are completely combined. So I should define what I mean here by a volcano. In most cases, it's really a volcano edifice. In some cases, I had to become pragmatic, like the Ingen stream dispersions. This is not a volcano, but a submarine area of many submarine counts. It was just for reasons of practicality combined as a single volcano location. So it's essentially this database, including the Alaska-Aleutians, was published a couple of years ago. It's in EarthChem. It's available. I have since done a little bit updating, but I didn't publish the updates. Sorry. But still, it's pretty comprehensive. It's not much more to be said about that. It's available. I'm not maintaining, but I'm not maintaining that what has been published. So I wanted send the rest of the talk. I want to give more what came an outcome with respect to crustal contamination. I was particularly interested whether these high silica rocks are sourced by the overlying crust. So a simple plot to make this, or the isotope data from the global arc, a simple plot to make was to plot the bulk rock silica versus the lead isotope ratios, assuming that the latter ones are particularly sensitive to crustal contamination. I don't know what I expected, but I did not expect what I got in the end. So on the x-axis is bulk rock silica, on the y-axis, I'm sorry, it's a 206, 204 lead. And you see that almost all volcanoes, all arc segments do not show any trend in the lead isotopes versus the silica content. Here on the right side, there are a couple of arcs highlighted. We worked a lot here in Mexico. It goes well up over 78% in silica content. Mexico is a classical arc building of continental crust and diverse continental crust of thickness between 30 and almost 50 kilometers, but there is no trend in isotopes with the silica content. The same, for example, for the Southwest Honshu arc, which is known for very explosive silica-rich eruptions. There is no apparent signal of the crustal contamination to be seen. The only exception in that globally I saw might be the central volcanic zone of the Peru, which is the the thickest segment of 70 kilometers of crust. There we see more diversity. It's a little bit outlier globally. But anyway, this was a typical signature that the lead isotopes and also the other isotopes do not change with increasing silica content. A first look on the Aleutian arc might tell us that there are variations, but the red one is now the eastern Aleutian, the blue one the western. But if you look, but this is actually a consequence of the well-known trend, spatially from east to west, that the lead isotopes of the arc decrease. That has to do with the slab input. That has, Peter Kellerman has this done quite a while ago. And if we resolve that on the basis of individual volcanoes, I went a little bit pragmatic with these red and blue circles. You see all the signs that with increasing silica, each volcano or volcanic location does not show any trends with increase in lead isotopes with increasing silica content. So we know that this has this is now plotted on the entire data, and you see they make a beautiful straight mixing line regardless of the melt silica content. There is no change. There is no need for fault filtering for the mafic melts. So it's a binary mixer between the trench sediment and also some mantle wedge composition. So in summary, this tells us, I concluded from that we don't have much need for crustal contamination in generating these high silica magmas. There is not the bulk of the silica is not coming out of the crust. Of course, we might have always some little crustal contamination. There might also a couple of arc magmas that have very strange signature. They might be contaminated, but not the bulk of the arc magma. So we are discussing now two azimuth differentiation models. On the one side, this is a classical model where we have a partial peridotite melt coming out of the mantle that evolves by fractional crystallization within the crust by polybaric, and then gets up with recharge melt mixing. But this model has well-known problems. We have never really fully observed the fractional crystallization paths. And I'm not speaking of the modeled one, but really of the observed. And we don't know where all these residual cumulates should go by the high degree of fractional crystallization these magmas mean. An alternative end member might be that these high silica magmas are created in the mantle wedge, and from a mantle wedge that has been reacted with the silica-rich slab melts, components that have been added. We know very well that if we add the silica-rich slab material to the wedge, the mantle reacts, the peridotite might not stay. There's a lot of things happening, and that these and more silica-rich melts can be created, and these go together with partial peridotite melt, go up into the crust and hybridize before they erupt. So the database outcomes as far as we have no support for extensive crustal contamination in creating high silica arc magmas globally, but instead we point to a control of slab and mantle fluxes, but we still need to really figure out where these high silica melts come from. And it emphasizes also a need of integrating these high silica rocks into the geochemical studies. They are part of the arc system. They are there, and they make the really dangerous, highly explosive eruptions. Thank you very much.